Welcome learners to the course on analog VLSI, and in the next few lectures I will try to cover the different aspects, precisely the design aspects of the operational amplifier, and if time permits then I will go for the detailed analysis of operational transconductance amplifier. So this will be a series of lectures, major consisting of say 6 to 8 lectures, where the first 4 lectures of this series will go on the operational amplifier, the design criteria and different sort of analysis, whereas I will go for the last 3-4 lectures on the OTA. Myself, Orpon Deashi from the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, India. Welcome you all to my lecture series on OPAMP and OTA. Other parts of the analog VLSI, which I have already covered in my different class lectures as well as in the web lectures also, and I presume that the concepts of the differential amplifier is well understood by all the learners. But so far, if you have some sort of doubts at precise, then in first few slides I will try to cover up the foundation of the circuit, which is the heart of the OPAMP, that is the differential amplifier part. And in this lecture I will basically cover the fundamental block diagram of the OPAMP as well as the different functionalities of the various building blocks of the OPAMP. And that's my ultimate objective of this lecture. Whereas in the next lecture I will go for the equivalent circuit and the design criteria. The lecture 3 I will deal with the details KCL analysis and the pole zero formation and how the things are going on. And in the lecture 4 I will go for the different topologies, like the so I will go for the topological parts, and then if time permits I will go for some numerical problems so that you can understand how the things are going on, how to calculate the different design parameters. And after that I will go for the first and second order of OTA based on various topologies. So that will be in some later part, but let me start with the foundation part in a more precise manner. And naturally, once you have accustomed in your preliminary level of courses on OPAMP, the most important part the teacher shared that the concept of virtual ground. If you have a clear concept on the virtual ground, it's very fine, but if you have some sort of doubt on the part of virtual ground, let me just briefly go through the part and I'll let a preliminary level sort of discussion on the virtual ground, and after that I will proceed for the what will be the actual functionalities of the various building blocks of OPAMP. So that should be the objective, and I always like to discuss about or mention about the basic objective of any short video lecture at the preliminary level, so that you can understand it in a more clear manner, and you will find that you will be more or less accustomed with that, and then you can proceed in a easier manner so that you can grab the concept and you can prepare for the next lecture of this series. So I'm welcoming all, and I'll start with the basic concept of the virtual ground. And if you go to my circuit, what I have drawn here, you will find it that the major part is nothing but a differential amplifier. And one significant point, if you look out, that the major thing of this differential amplifier is that it is not made of say called BJT, as you will be familiar in most of the cases in the exercise book what you have found. This differential amplifier is made by MOSFETs, two N-channel MOSFETs. So let me first briefly describe the circuit, and then I will analyze that how it can be modified in the form of OPAMP and how the concept of virtual ground is embedded in the circuit. So I first preliminary level describing that both the drain of these MOSFETs are connected to VDD by naturally drain resistances, and two different voltages are applied, and significantly what you are getting at the say source terminal, source are connected, they are short circuited and connected to ground, and naturally the connection point of the source I designate by the point P. Actually you will find that a circle of bluish circle is designed at the background. And since Vi and Vj are different and R1 and R2 are different, so it's very easy for you to understand that naturally the biases or the current flowing through the say two resistances I1 and I2 should not be same, it should be different, and that's very simple because why you will get the same output, it should not be, the outputs are different, and that means what you are doing with the functions, that means if they are different then it is a question, serious question, that two different outputs, that means the currents are not equal and you are getting some sort of unequal current flow in the two MOSFETs. Mind it, at this condition we may assume that both the MOSFETs are on. It's not mandatory, but if you make one MOSFET off, then it is very simple that the total current will naturally flow through the other MOSFET, and that doesn't require any hard analysis. It's very simple to all of us to understand that if one MOSFET is off, naturally the current flowing through the other MOSFET will be significantly high, and naturally it may happen for both M1 or M2. But if both the MOSFETs are on, then Vi and Vj, if they are very close, then R1 and R2 are also very close. If you assume, then it's very simple that you may assume that I think that the current ID1 and ID2 are very close to each other. So if that situation happens, then ID1 and ID2 are very close to each other, then the sum of the current, now at that case if it is Is, and if one MOSFET is off and another MOSFET is say on, then the sum current Is, that should be same. Why? Because the source of both the MOSFETs are connected to the point P. So the summation of the current flowing through the MOSFET should be equal. I am not saying that the individual current should be equal. No, not necessary. They will be equal if all the parameters of M1 and M2 are same, R1 equals to R2 and Vi equals to Vj. But otherwise, but whatever be the criteria of Vi or Vj, naturally you should consider that the sum of ID1 and ID2, that should be equal, and that's very very important if you when you go for the analysis part. So if that is the matter, then the point P, how could you ensure that the current through the point P at different time interval or at different condition of the biases. Biases means I am saying the Vi and Vj at different conditions of Vi and Vj, the current flowing through the point P should be constant. How could you presume that? So in order to understand that the current should be equal, what we will try to make that the current can be constant, then you can assume that there is a current source. that means a current source present between the common point of the sources with the ground. That means between P and G, G is my ground point and P is the point, the common point where the sources are connected. And significantly, the IS, that is the sum of ID1 plus ID2, which is shown in the previous slide. So, if I consider a current source, then there is a function. A very important concept it will come. The current source gives a constant current, which means and it has a zero resistance theoretically or ideal resistance, which means as per Ohm's law, the potential at point P and potential at point G should be numerically same. This will not happen if you replace the current source by a resistance. No, never possible, because resistance means the potentials will be different. But if you connect 2 points by a constant current source in any electrical circuit, then the potential of those connecting nodes should be numerically same. But the point you have to presume at this juncture is that G is your ground. There is no problem on that. But P, though its potential is numerically equal to the ground potential, but it is not directly connected with the ground, because it is connected with ground through a constant current source. So what we can tell that if it is connected with a constant current source, then there is an element, an active element, so P can't be considered as a ground. At this point, the PL point is called virtual ground. That means P has the same potential, or virtual ground has the same potential of ground, but it is not directly connected with the ground. It is connected with the ground by some other elements, by some circuit elements. And that's why P is called virtual ground. And the circuit element should be a constant current source. There are no other options. So virtual ground is a point in an electrical circuit which is connected to the original ground point through a constant current source. And how could you realize the constant current source? Because what I am drawing is the symbolic representation. So if you just replace it, the constant current source, by some, say, MOSFET whose drain and gate are shorted, then the MOSFET will work as a two-terminal device. It's very simple. And if you short, say, drain and gate, then it is very easy that the MOSFET will behave as a constant current source. It's simple, because you have a single input contact and that is connected with the point P. So practically we require 3 MOSFETs and 2 resistances and a source point, which is VDD, in order to make a differential amplifier. What type of differential amplifier? Which consists of both virtual ground as well as the actual ground. And that's the heart of your operational amplifier. I'll come in the next slide a little bit later on. But that should be the case of a differential amplifier circuit. And that is the most significant concept while we will go for the mathematical analysis for different circuit related perspectives of OPAMP. So I think the concept of the virtual ground is clear, and naturally from this concept we will bring the definition of OPAMP. And how the definition of OPAMP will come? Naturally, if you have considered or design an amplifier, whatever the differential amplifier, amplification means it should have a gain. And naturally the gain should be forward gain and it should be high enough. Otherwise, if you make an amplifier which amplifies 1 to 1.001, it should not be an amplifier for bulk circuit perspective. But it should have a high forward gain. Now, how could you make a stabilized gain of an OPAMP? or say any amplifier. For stabilizing the gain, you require a feedback circuit, and simply the feedback should be negative feedback. I think the basic foundation of the electronics engineering course is already covered by in great details by the teachers of any universities, colleges, or institutes. So you know that negative feedback is one of the fundamental criteria in order to stabilize the gain. Now, if you apply negative feedback, naturally the relation between the input and output, nothing which is in alternative way called the transfer function, the closed loop transfer function, it's simply the negative feedback, it should have a closed loop transfer function, because you can't say the open loop transfer function. The transfer function should be closed loop. And what will be the value? You know that will be normally called by A1 plus A beta, like that format. That's the standard notation I am taking. And that transfer function obviously becomes the independent of the gain of the circuit. So naturally, for any amplifier where the closed loop transfer function should be independent of the gain of the circuit, then how could you lock this range? That means the fluctuation or the variation of the transfer function within a very small range, and that's why you can't be allowed to vary the input voltages too much. That means the input voltages should be within a very specific range, and that's why output will be controlled precisely by the input voltages. So that's why it's a voltage controlled voltage source, and that means you have a controlled sources. So the controlled sources are the input, the gate bias of M1 and M2 as per the circuit I have drawn already. So these control sources are very important, which gives you a high forward gain under the consideration of application of negative feedback, and the transfer function, which is obviously the closed loop transfer function, should be independent of the gain of the circuit. And that becomes the definition of OPAMP from the analysis, the basic analysis of the virtual ground. Now, I am going to the basic block diagram of the OPAMP and how could you proceed for that. In that figure, you will find that there are 5 standard blocks of the OPAMP. One will be the differential transconductance stage. One will be the high gain stage. One is the output buffer. One is compensating circuit, and another is biasing circuit. Obviously, I will discuss why I am writing these stages only, and then in next few slides, I will discuss the exactly the functions of each individual stages. And mind it, in the point of compensating circuit, there are 3 different compensating circuits, and I will discuss the function of each and every compensating circuit. So first, I am telling why I am writing a differential transconductance, because if you calculate the voltage gain of a differential amplifier, you know the DC voltage gain is minus GMRD. Forget about the negative sign, it's just a phase reversal. So I'm not going into that. DC voltage gain is not the phase, but the sign comes because you are taking the input and output of the different magnitudes so far, so plus and minus factors. So I'm not going into that because there's a sign reversal actually, sorry. But because it's everywhere, if you go for small signal analysis also, it will be GMRD minus. So transconductance and the drain resistances are the 2 fundamental parameters, and naturally we are going for the differential transconductance stage, where I am giving 2 input voltages, the Vi and Vj, as per our previous circuit. And naturally the gain of a differential stage may not be very high. So what we have to do, we have to boost it up, and that's why we require a high gain stage. And there may be a chance of the variation of phase for any sinusoidal wave. For example, ideal case, fluctuation of the frequency or the current flowing from the circuit. So we require the compensation of all of them before getting the final output. So we require the current compensating circuit, frequency compensating circuit, as well as phase compensating circuit. And all will be connected by the biasing circuit, by differential transconductance and high gain, and naturally everything will be connected with the output buffer, because end of the day you require a buffer to produce the output, and it's very simple, so that we are also going for an output buffer. Thus compensating circuit may be, some textbook says directly connected with the high gain stage, some textbook says no, it is connected through the differential conductance stage. So it may vary. You can also make a connection between the compensating circuit and high gain, maybe, may not be, but somehow it may be related or like that. So I am going to the discussion of each and every stages. So these are the name of the stages I have written here, and please everybody requested to look at the point 4 where I have written the current, frequency and phase compensating circuits. So with that consideration, I am going to first discuss about the function of the differential transconductance stage, and it provides the differential to single-ended conversion. You know that there is a single output in the op-amp and two inputs, so naturally it will be a differential to single-ended conversion. The differential input voltage, it produces the output naturally, so it should be a voltage controlled voltage source. I have already mentioned it, and a part of the overall gain is already provided by this stage, but it consists of noise and offset and all those things, and the offset nullification concept I will discuss in my lecture 3, so by KCL analysis. So till now hold the offset point, and that though it provides gain, but obviously gain with accustomed with some losses, and that includes the noise parameters also. Next I am coming to the compensating circuit, and first I will discuss the phase compensating circuit. So it is a circuit which responds to the input just by changing the input voltage of the differential transition. Why? So that the phase reversal can't take place across the resistances. You don't want any phase change in that case, or if that occurs, it should make a transfer to the previous original cases, and that's very much important for making a phase compensating circuit. Similarly, if I go for a say current compensating circuit, then it responds to the input by modifying the bias current, so that amplifier is not latched. I think the concept of latching is known to all, and if one it's a memory sort of element, so amplifier should be dynamic. It should respond to the change of input voltages, and that will be one of the fundamental criteria, and that makes ensured basically by say current compensating circuit. And then I am going to the say third compensating circuit, which is nothing but the frequency compensating circuit. So it is basically required to prevent the overshoot and the undesired oscillation at the initial level, and so that it should not go for the unstable condition, and that is ensured by the frequency compensating circuit. Next I am going to the function of say high gain, and naturally if the gain of the differential amplifier is low, then it should be raised, and you require some booster or some intermediate amplifier stage, and this is also covered in our behavioral circuits in analog electronics course. So the high gain stage, it amplifies the transconductance output and fed to the output buffer as already shown in my block diagram. Then I am coming to the case of the output buffer. So naturally it should have to stabilize the output of the high gain stage, and it provides the bandwidth. This is one of the very key part. You know the gain bandwidth product is constant. So if there is enough gain, then the bandwidth becomes low. It should not be demanded. So what will be the maximum level of the gain? Because if you have to set a predetermined say bandwidth, then you should know that my gain I can't allow more than that. So that will be totally ensured by the output buffer, because once gain is fixed, then you know this will be my actual bandwidth I am obtaining. And then I am coming to the last part, which is the function of the biasing circuit. So it provides the biasing to all those stages, the differential transconductance, the high gain, the output buffer, so everything it provides. So naturally you require the biasing arrangement, otherwise your circuit will not work. So that's the fundamental parts of our the basic building block of the op-amp and the functions of the different circuits. And this compensating circuit sometimes also may be connected with the high gain stage, but maybe directly or indirectly, but ultimately it provides the stability. So it provides the stability either to the differential transconductance stage or to the high gain stage. Not too much to be worried of. So till that, thank you all for attending this lecture, and up to that we have discussed the basic part. In the next day I will go for the design consideration and equivalent circuit of the op-amp. So thank you all.